This is a really basic introduction as to the overview of what a numerical method might be. Um, in essence, a numerical method is not utilizing analytic methods to be able to solve an equation or to be able to solve a system or to be able to solve a differential equation or to do a derivative, those sorts of things. So a lot of times in mathematics, we can't necessarily utilize analytic values. We have to use approximations. And especially in like our calculators, like your TI-85 or TI-86 or whatever you might have, um, one of the ways that we can represent an infinite trigonometric function is by using an infinite series. So for those of you that have taken Calc 2, you probably remember seeing something like this. You might not remember exactly what it is, but the cosine function can be represented by this alternating power series. All right. And what happens is as you fill in values of n, so this summation means you're going to fill in a 0 and then a 1 and then a 2 and then a 3 for n, and you're going to get a polynomial for that. And we know polynomials are much easier to work with than trigonometric functions, logarithms, exponential functions, those sorts of things. And what we'd like to do is we'd like to be able to use MATLAB to be able to approximate and try to view what the effectiveness of this infinite series is as we start to expand the polynomial. Right? So let's go ahead and use MATLAB. We're going to prompt the user to enter a number, and we're going to find the cosine of that number. We're going to print it out to 15 decimal places, and it's going to be approximation of the cos of n, not the root, found by this by the series in MATLAB. All right, it's probably what it says. So this is the version you will see. I'm just kind of revising it and going a cut and paste from other things, so I apologize. Then we're going to approximate the value of the cosine where x is going to be the user input. And then we're going to have n equals 1, n equals 2. So we're actually going to have 7 outputs. And as n increases, this increases the order of the polynomial. We're going to compute the percent error. And then finally, at each step, we're going to print the order of the polynomial. All right, so there's a lot going on here, but it's really not that tough. Okay, it might take us about 10 minutes to actually write the code for this. All right, so first thing we're going to do, we're just going to, the only input we have is just getting the value from the user. Okay, so let's call n, or let's call, yeah, I'll just call it n, is going to be equal to input, and we're going to say enter the value of the cosine. Well, let's say enter the value of n to find cos of n. All right. And that's literally the only input we have. Now, I'm going to go back to that formula and I'm going to define our 7 polynomials. All right, because the whole idea of this is to get 7 polynomials. And what I'm going to do is I'm going to shove in 0 and then 1. And remember, our summation means we add 0 and 1 if n were 1, and then 2, and then 3, and then 4, and then 5, and then 6. All right, so let's just go ahead and do that really quickly. And I might need to use a calculator for some of the higher order stuff. So P0 is going to be equal to, so this is where we just have minus 1 raised to the 0 times, now we're going to have x, which in this case is n, the value. So actually, maybe I could just call this x instead, just for clarity. Not that it matters much, but times x raised to the 2 times 0. And then we're going to divide that by the factorial of 2 times 0 in this case. All right, so I'm just going to go ahead and run this really quickly just to make sure that the fact function works. I'm pretty sure it does. So that doesn't matter. No, it doesn't. All right. I wonder if it's factorial. Yep, okay. So P0 is 1. All right, so at least we know that all works. And now what I'm going to do is I'm going to define this again. So this is going to be P1, and P1 is just going to be the previous And all I'm going to do is just change all of the zeros to ones. All right. And let me just run this just to show you what this looks like. All right, so run, and let's say 3. All right, so right now, this is really not a good approximation for cosine of 3. All right, so, but we're just going to keep doing this. All right, so it says to do it up to 6 times. All right, so it's going to be a lot of full work here. So this is going to be P2. Right, and I'm just changing all the ones that I had to 2s. All right, and you can see where this is going. Now this is going to be P2, and I'm going to copy P2. We're going to see later in the course that there are ways to make this a little more efficient. So this would be 2 times 3. Oop, that's going to stay 2 times 2. I just have to copy this. All right, so I'm going to make that a 3, and then this a 3, and this a 3. All right, and so it's really a 4-term polynomial. So let's go ahead and run it. And so now it's getting a little closer. All right, but as we go out, it's going to get a little bit better. All right, so we have 4, 5, 6. All right, so with 4, we have to go through and change all of these 3s to 4s, and we're adding it in each time. So this is probably really taxing watching me do this, but, and we're going to copy this guy. So we need that, and we need that here, but we need to also add in 5. And then finally, we're going to add that, and then we have a 6 in here. All right, now, assuming that I haven't made any errors copying, pasting, all right, that's a big assumption. So I'm going to run through this really quickly just to make sure. All right, so the only thing that we have is x consistently the whole time. That's a plus there. Just to make sure, and there's a plus here, which probably means in some of the other ones I need a plus. And it's a 4, good, 3, 2. All right. And we could check what P6 is. So let's go ahead and execute it. All right. Now, the true test is, well, what is the cosine of 3? Right? So I'm going to run this. Now notice that these values are really close to one another. Thank goodness. Because otherwise we would have to redo the whole video. Well, you wouldn't have, I would have had to. And that's what it's supposed to do. It's that this polynomial, as it starts getting bigger, is supposed to be closer to the actual value. All right, so the actual is going to be equal to the cosine of 3. All right, so that's, or cosine of x, excuse me. All right, now we have to go through and let's check our instructions. All right, so we're going to get, we've already done part A. We're going to print out the approximation to 15 decimal places. So let's do that. So we're going to do an fprintf, and we're going to say cos, and I'm just going to say percent f to 15 decimal places is percent 0.15 f. And we'll close that out. Well, we're going to do backslash n and close it out. All right. And I have to put the parameters. So that's going to be x and then the actual, or the actual. All right. So let's just go ahead and run it just to make sure before we go any further. And I'm going to suppress this guy because we already know it works. Again, thank goodness. All right, so we're just going to run it, and we have 3, and we have cos of 3 accurate to 15 decimal places. Okay, so that looks good so far. Now, approximate the values of cos x. All right, so we've already done part C. That's what all that P0, P1, P2, etc. is. Compute the percent error at each step. All right, so we're going to have a number of errors in this. So I'm just going to call, we have E0, and E0 is going to be equal to the absolute value of, now this is going to be P0 minus the actual divided by actual. Right, so that's how we get error 0. What we're going to do is we are going to copy this 6 times. And we're going to have error 1, 2, 3, 4, 5, 6. And we're surprisingly, we are going to change this to 1, 2, 3, 4, 5, 6. So here's our errors. So this is the error of polynomial degree 0. This is the error of polynomial degree 1, and then error of polynomial degree 6. All right. So that's good. So that's done. So now we've computed the percent error. And now finally, we just need to go through and print out. All right. So it says during each step, print the order of the polynomial, print the approximation, and print the percent error. All right. So let's do an fprintf. And we're going to say at iteration 0, all right, or we could just say at degree 0, at polynomial degree 0, the approximation is, we can say percent f or percent 0.15 f, and the error is percent 0.15 f. And we're going to do a \n. And the only 2 things we're calling is we are calling the polynomial degree 0 and we are calling the error. I'm going to call that E0. All right, now let's just make sure it works before we go any further. So we've been using 3, might as well. And it's P0. I might have used P0 instead of the 0. Okay, there we go. And let me make sure this one's okay. I think I accidentally used the letter O instead of the number 0. All right, so let's try it again. All right, so and I probably should multiply these by 100%. So let's just do that for all of these because I think it says find the percent error. And the error is, all right, so let's run it one more time. All right, so at polynomial degree 0, so that's our iteration. The approximation is 1, which doesn't make any sense. That it's a good, let me rephrase that. It makes sense, but it's not a good approximation. And we have a negative 200% error. All right, so that's not good. I should probably do absolute of the actual as well, because it doesn't really make sense to have a negative. So no big deal. Because I remember the actual value was indeed negative, and we want to just make sure that. Okay. So this should give us a positive value. All right, so 201% error. Certainly wouldn't want that to happen with my paycheck. Now the good news is, all we're going to do is just copy this. Let's see if I can undo that. I hope I can undo that. I might have to reprint it. Oh, bummer. Yep, I accidentally pasted instead of cut, so bear with me. fprintf. You can just fast forward a few seconds if you want. At polynomial degree 0. The approximation is %.15f. And the error is %.15f slash n. And we're calling P0 E0. All right, so we run it again just to make sure. There we go. Okay. Now this time, I'm definitely going to copy and paste. And we're going to do that. All right, so now we have degree 1, degree 2, degree 3, degree 4, degree 5, and degree 6. All right, and we're just going to change all of these accordingly. So that's going to be 1, 2, 3, 4, 5, 6, and finally 1, 2, 3, 4, 5, 6. All right, so let's see what we get. We've got a whole bunch of code here, and we don't have to suppress the output, no big deal. So let's run it, and let's find the cos of 3. All right, and the good news is, all right, so here's the actual value. So cos 3 is negative 0.9899. All right, so here's 98992. Here's 98993. All right, so as we keep getting more terms in our polynomial, we keep getting a better approximation. All right, so pretty cool that we go from 200%, actually 253%, down to 0.005%. All right, and I should probably put the word percent in there, so that way somebody that's looking at it, so just to kind of make sure that this is good. So I can run this again. All right. Just to show you that it does work for other values. So because we've been using 3 the entire time, now it's really cool that we can insert any value we want for cosine. So let's say the cosine of, let's say, I don't know, pi over 2. All right. Now this one doesn't work too well for some reason. I think it's because it's an exact value. And as that polynomial starts getting bigger, then not so nice. All right, so let me run it again. Let's do something like 15. All right, and it's not giving us nice values for this. All right, so that's not good. And I'm wondering if up in here, either something's saved incorrectly or something's not working too well. So it works for 3. Works really well for 3, but when I plug in something like 4, it's not too terrible. It might just be the value of the polynomial. All right, all these numbers are different each time. For 1, it works really well. It's probably because it's centered about 0. So if we were to change it around and get more terms, as this expands, it probably gets a little bit better. So if I did something like 0.05, all right, notice that this is really close. All right, so it's probably because the Taylor series or the power series is centered about 0. And as you start deviating from 0, the values just start getting a little bit less likely to work too well. So for instance, like if I was to plug in something like 0.0001, check how quickly this starts converging to a really close value. So it's pretty cool. In real life, if you wanted this to work a little bit better, what you would have to do is you'd have to use a lot more terms, so that way you could probably get a better approximation for this. All right, but if you were to use something like 100, the error is just pretty astronomical because obviously 100 is really far from 0. Right. So hopefully this gives you a good overview as to some of the capabilities of MATLAB, and then some of the uses that we're going to be going through for formatting, input, output, etc. throughout the semester. In the next section, what we're going to do is we're going to start exploring graphs. We're going to start exploring file input and output, and being able to read from a file, etc.